Good morning, good afternoon, good evening. Might even be middle of the night for some of you. Thanks for joining us today. DCT 302 session 5. And I'm delighted to have you here, and I'm delighted to have you asking some questions and making some comments in the forums. I've got one or two loose items left over from a day or two ago, and well, a week or two, I guess. The big item would be um, f-stops. Now, Peter Rixner, I see you're with us today, and this is your question. So thanks for asking for clarification of that. And let me see if I can do a little improvised explanation of that issue. And we'll improvise even a blank piece of paper to start that discussion. Okay, so we started this discussion with that the scale that I showed you. I think it might have been class class 2, I think, or maybe class 3. And that scale showed you linear light values. And I showed you a log scale. And I think that went for 3 decades. So I showed you numbers from 1 to 1,000. And I think at that time I indicated to you that a stop was a factor of 2. So starting at the top, that would be the difference between 500 and 1,000, which is a ratio of 2. And it takes 3 1/3 of those ratios to get to a power of 10. So 2 raised to the power 10 over 3, in other words, 2 to the power 3 1/3 is 10. And that means that there's 3 1/3 stops in a density unit. So it's a log scale, and we might find on a practical camera that the numbers might go up to 4,000 if it's a 12-bit camera. But we'll stick with 1,000 at the top end of the scale for the time being. So let me switch colors, and then I'm going to try to improvise another scale, which is the scale of powers of 2. And I'm going to write that on this side of the diagram. So I'm going to go down 1, 2, 3 1/3, and then 1, can I do it? 2, 1, let me think, 1, 2, yes, that's it. So we go down 1 stop, 2 stops, 3 stops. 3 1/3 stops is 1 density unit, or 1 factor of 10. Then we go down, well, what I should really do here is I should do separate this out in steps of 10 stops per decade. And there's a little trick to doing this. Okay, so now 1, 2, 3 1/3. Okay, I think we've managed. So this is in terms of stops. We go 1,500, 250, 125, 63, 32, 16, or some people would write it 15, 8, 4, 2, 1. So you can use whichever of these schemes you like. This is a stop. This is a density unit. Now, the question that Peter was asking has to do with apertures.
Change the input.
And I'll ask somebody to mute their mic. We're getting a little extra background noise here. Thank you very much. So we were discussing f-stops, and let's start with we'll start here at this exposure level, and let's draw an aperture like so. So all of the light entering the camera is going through this aperture, but it's adjustable. And to give you a little tiny introduction to optics, we've got a complicated lens system here, potentially very complicated, but I'm going to draw it just as one lens element. I'll draw a center line, and I'll indicate that light from the scene gets captured by the lens and focused, sort of like so. And we talk about the focal length of the lens, and we give that the symbol F. And it's a certain number, like maybe 50 millimeters. And that is actually the measurement of how far back from the center of this simple lens you find the image plane. And if light comes in from a different direction here, like light coming from this direction, will get collected and focused sort of like this. And this particular example, it's actually focusing outside the dimension of the image area. But, that's allowed. That happens. Light comes into the camera from all sorts of different directions. So the symbol F, we call it the focal length of the lens. And there's another really important parameter, which is the diameter of the lens. And I'm going to give that a symbol D. And the diameter of the lens really determines the light capturing ability of that lens system. So the larger the diameter, the more light it captures. And we rely on the optical system to convey that light to the image plane and put it in the right places. So here I've given you this dimension D, which is the dimension of the lens opening. And you can see from my sketch that I just happen to have chosen an example where the lens diameter D is roughly half the focal length. So let's say 50 millimeters, or in America, about 2 inches, but this lens is only about 1 inch in diameter. So we have a situation where D equals F over 2. In other words, the lens opening is half of the focal length. That's the notation we use to describe aperture. So aperture is just the opening, the lens opening. And we always describe those openings not by their absolute metric dimensions, like in this case it would be something like 25 millimeters, but we don't use that dimension. Instead, we describe the aperture in terms of its ratio with the focal length. So an aperture of f4 would have an opening here only half this dimension in my sketch. Now, as we all know, we don't typically change the glass out to change the aperture. Instead, we rely on the lens to have a variable element somewhere in the middle of the lens that stops light at a certain extent. So this element in the lens is called the stop. Why? Because it stops light. It's as simple as that. And it's adjustable, and there's a ring on the lens typically that alters the size of that opening. And we calibrate that opening in terms of f-stops. Now, the question that Peter had the other day was, well, how do those f-stop numbers relate to this scale? Because, Charles, you've said that the stops on this diagram go down in factors of 2, and you've said that the stops are related to the light power. So if I've got the difference between 1,000 and 500 in terms of light power, that's one stop because it's half the power. And the question was basically, how do those numbers relate to the stops? Well, the relationship is quite simple, but it took me a while to figure out how to explain it clearly. And that's, of course, what I'm doing now. So basically, here I'm showing you, we'll just start with this example. This is going to be f over 4, and it's got a certain diameter. Now, obviously, f over 2 has got twice that diameter. However, the amount of light that enters the system is proportional not to the diameter, but to the area. And area, well, if you remember from high school math, area is pi r squared, where r is the radius. Well, but we're not really talking about the radius here. We want to talk about the diameter, and that's twice the radius. So instead, we have to say pi times the diameter over 2 squared, but that's equal to pi times d squared over 2 squared, which is to say that it's pi times d squared over 4. In other words, it's about 3/4 of the diameter squared. So what that means is that F2 lets in 4 times as much light as F4 on the aperture setting. So if we want an intermediate situation here, we need to pick a number which, when it's squared, well, if you square that, the diameter of this is 1/2. The diameter of this is 1/4. We need to pick a diameter which is midway geometrically between those two. And that diameter works out to be 2.8. It's 2 times the square root of 2. And so it's the 2.8 setting that if you had the same amount of light coming in through all 3 of these apertures, and let's see if I can draw that. So consider the same amount of light coming in and run through these different apertures, it would drop the exposure in factors of 2 each time. So let's do a couple of apertures on the bottom end of the sequence. If we went from F4 and we have that and we went to F8, now it gets fairly small, half the diameter of this. But again, that's 1/4 the amount of light. So where the F4 aperture was taking us to this level, the F8 aperture will take us to this level. So we want to have an in-between condition, and this works out to be F5.6. So these numbers on the denominator are doubling, but they represent 2 stops. So this is called a stop, this is called a stop, this is called a stop, this is called a stop. So these numbers are doubling. These numbers are also doubling. So the next number's up, well, we round this off to 11, and the next one will be 22, and the next one is 45. So the rounding is a little wacky. But then F8, the next one, just doubling that is 16, doubling that is 32. So there you have it. That's how you get the stops relating to the F numbers. And then a typical lens aperture ring, it'll have, obviously, as you all know, calibrated settings. And they will typically, well, they will have little detents. So as you rotate that ring mechanically, it will drop into a little slot at each of those positions. But it's also very common to have two intermediate positions. And why are there three settings for each stop? Well, it's because this relationship between the power of 10 and the power of 2, there's 3 density units for every stop. So three units, I'm sorry, 3.1 units. There's 10 density, 10 units for every density unit, 3 units for every stop. So it's usual to have adjustments of aperture at 1/3 stop intervals, and interestingly, not at 1/2 stop intervals, generally at 1/3. Okay, so I hope that covers it, Peter. It took me a while to figure out that explanation, and I had to kind of spend an hour at the cafe to remember exactly how that works. Okay, so with that, let's see. I think I had one other issue that I wanted to explain kind of spontaneously as we go, and I'll take the opportunity of having this blank slide in front of me. I want to say some things about dynamic range. So we had in the previous slide that big ratio of 1,000 to 1 of code levels, and I set that scale up logarithmically because, very roughly speaking, we see logarithmically. So we kind of see in stops. And in cinema, it's absolutely common to deal with log acquisition formats. So slog, RE-log, RED-log, SI-log, and so on. Logarithmic units are absolutely common in acquisition, but at display time for HD, we don't use log coding. We tend to use power function coding. So on the output end, as you know from previous classes, the response of the display is typically the video signal raised to a power. And so the front end of camera processing is generally some kind of inverse power. So the mapping from linear light tristimulus value to video code is something like the inverse of that. So you could very roughly say that at the input side, voltage, and these are scene tristimulus values because we're scene referred. So you could very roughly say video signal is linear light to the 1/2.4, something like that, which is comparable to linear light to the 0.42 or the 0.45 or the 0.5. Some number like that would be appropriate for the front end of HD. But again, cinema, we typically do log processing. So we're relying on the DI processing chain to take that log data, and at some point in the chain, when we're distributing to HD, somebody's got to do this conversion. So in cinema, the curve we use is more like a log, but it has a very close resemblance to the power function. So the processing in the DI chain, though, will differ. But now getting back to the issue that I want to talk about in some detail, you could say that in this situation, if you've got image data which covers that whole range, then you could say that the contrast ratio is 1,000 to 1. Although really contrast ratio is really a term that's best suited to displays. And at other parts in the system, particularly out in the scene in front of the camera, it would be better to use the word dynamic range. Now, just to warn you, in terms of dynamic range, so if you think of this scale of 1,000 to 1 taking place out in the camera. This is 1,000 to 1 is 3 decades, 3 factors of 10, in other words, 10 to the third. But the photographers would prefer to refer to that as 10 stops, whereas stop is a factor of 2, in other words, 2 to the 10th. And those are very nearly equal. 2 to the 10th is actually 1,024 instead of 1,000, but they're so equal that it doesn't really make much difference. Now, there are cameras which claim more than 10 stops, like 11 or 12 or maybe even 13. So you can also call that dynamic range. And as if decades and stops weren't enough, we've got another unit, which is the unit that the camera sensor vendor would prefer, and that's decibels. And in the decibel scale, there's 20 dB in each decade. So in other words, at 1,000, that corresponds to 60 dB. 100 to 1 is 40 dB, 10 to 1 is 20 dB, and we start at 0. So there are some camera vendors who are claiming 66 dB dynamic range, and that would correspond to 11 bits. 60 dB corresponds to 10 bits. So that just gives you a little bit of information on the dB scale. So contrast ratio we should reserve for displays. Dynamic range is more useful to talk about performance in the scene or to talk about linear light performance. Okay, here's the story. I want to tell you all about dynamic range. So let's imagine a screen, an HD display. And imagine for a moment I put up a white patch and I put up a black patch. And it would be completely reasonable to produce a white at 220 nits. Even a studio display is capable of doing that, although for a studio display, you'd be more likely to set it to 100 nits. Unfortunately, there's no standard for this at this instant, but that's the common practice for HD mastering. Now, if this is a consumer display in a somewhat bright ambient environment, then you might get a black reading of 1 nit. And that's partially because there's ambient light bouncing off the screen and raising the black level, partially because the LCD itself doesn't completely attenuate the backlight. So you're going to get some light coming through that pixel. You'll also get some light being bounced off the front of that pixel. Now, to compute the contrast ratio, that's simply the maximum luminance produced divided by the minimum luminance produced. So in this case, 220 to 1, which is a reasonable contrast ratio. It's not that great. If you had a contrast ratio of 1,000 to 1, you'd call that great. And if you had a contrast ratio of 10 to 1, you'd call that terrible. So let me put those two numbers up. So 1,000 to 1 would be great, and 10 to 1 would be poor. Okay, now there's a wire coming into that display that's carrying the signal, and I'll draw a connector on the back of it in the old-fashioned way. And let's say for the moment that that's a DVI connection, which is limited to 8 bits. So there's an 8-bit connection. And that DVI interface is connected to the output of a graphics card, and let's use the old terminology frame buffer, which is also an old frame buffer. It's 8 bits. I mean, today it would be 16 bits, And today we might have HDMI instead of DVI. But let's just use the 8-bit example for now. So those luminance levels are associated with numbers across the wire. And let's say for the example for the moment that the number that represents black is 1 and the number that represents white is 220. Now that white value could go up to 255 and the numbers on the wire could go down to 0. But let's say those are the numbers for the time being. So you might think to yourself, well, okay, that 220 divided by 1, that's just the contrast ratio. But it's absolutely not. And the reason that it's not is that at the display itself is taking those video numbers, which I always like to put on a scale of 0 to 1 because I'm a mathematician. But in terms of the integers on the wire, this might be 1 to 220 or 1 to 255. And the display is doing this power function that I keep fetching over and over and over. So the amount of light produced, the tristimulus value, is V on the 0 to 1 range raised to the 2.4 power. So what you're getting for code level 1 is absolutely not anywhere near 1/220th of the light you get at maximum value. In fact, let's go and compute that. So let's compute 1, and I'm not using 0 because if I were to use 0 in the denominator, this number would blow up and would either turn into infinity or error or overflow or some other number. So I'm using 1 just to avoid the calculation blowing up. And this 8-bit scale, of course, ends up being 255 over 255, so V equals 1. Here, V equals 1 over 255, which is about 0.004. And the amount of light we get here is 0.004 raised to the 2.4 power, which when I pulled out my calculator a moment ago, and you could do it yourself if you wish, just compute 0.004 to the 2.4 power, I get about 0.00016. So this is not, it's a little bigger than 1,000,000 to 1. So this is not 1,000,000 to 1 contrast. It turns out to be about 600,000 to 1. So there's some people who say, oh, 8-bit frame buffers, 8-bit interface, 8-bit image data stored in files, it's all terrible because the dynamic range is terrible. And that message, which you may have heard before, is basically completely wrong. In fact, an 8-bit frame buffer is capable of a contrast ratio of 600,000 to 1. Now, of course, we would like 10 bits in the studio video interface. So HDSDI interface always has 10 bits, but it's still underneath this curve. And so in a 10-bit interface, the numbers get even better. It's now 1 over 1,000 raised to the 2.4, which is an unbelievably huge number. So the lesson to take away here is that the dynamic range of 8-bit video is not limited if it's living under a power function curve or under a log curve, which would be typical of digital cinema acquisition. So there's no simple answers here. You've got to work through the numbers. But this relationship is the quick way to work through the numbers. Now, the other thing you have to keep in mind is that I showed you a DVI interface at first, but now if I strike that out and say HDMI, now we can have YCBCR numbers across the interface, where black will be coded at 16, white at 235. Well, you can't go dividing those two numbers to get the contrast ratio. That's not meaningful. First of all, the first thing that the display does is it subtracts the 16, and then it raises the video signal to that power. And that may be selectable. You may have 2.2 in an sRGB or 2.6 in digital cinema. Okay, so there's my explanation of dynamic range for you, and I think it's a super important issue, and I wanted to tell you about that. And Jefferson is commenting to us all. Of course, the numbers that I'm referring to here in contrast ratios like 1,000 to 1, 200 to 1, 10 to 1, these are the numbers that you actually measure with a color measuring device. And the numbers that they put on the box or on the spec sheet, they're completely different. Like Sony might say a consumer OLED does 1,000,000 to 1 contrast ratio. Well, these numbers just can't be believed. They're not measured in any sort of reasonable way. Okay, so there we go. That was a longer explanation than I had hoped, but a really important one. Now, I would like to go back and pick up from the previous session on some color issues. So let's see if I can go dig those up, and we'll do maybe 10 minutes of those and then 10 minutes of questions, finishing right around the top of the hour. So I think we were basically finished the big color science business. So we're and I'll just leaf through those slides that we did last time. We did all this business last time, and we did all this business, and we're headed toward representing color in a somewhat different way. So when we're talking about CIE little x little y chromaticity coordinates, like the famous diagram, that diagram is used not only for image science purposes, but also for industrial purposes. So this diagram shows you the colors that are standardized for signal lights. And it happens to come from the railways, but it is an international standard. And so according to the international standard, red has got to live in this area of the chromaticity diagram, like a red stoplight. A green light for go, a green traffic light, has got to be bounded in this region. See if I can draw myself an amber light. I don't see the word amber here, but amber would be kind of in this region, and that's sort of an ambery orange color. Yellow is going to be somewhere in here according to the standard, and finally a blue signal lives in these coordinates. And in Europe you'd use this for an ambulance or a police car. In Canada you'd use it for a snowplow, flashing blue light. Now, I hope you're wondering from this diagram, why is it that this green area is so big compared to the red area? And the answer is the little x, little y diagram is not uniform for perception. And it's very, very, very useful to find a way to make it uniform. And that's the purpose of the CIE LAB color space. So let's go there and look at LAB. So it came from attempts like this one to carve out little pieces of paper which corresponded to the distances in that diagram that you could just barely distinguish the colors. So one just noticeable difference, or JND. And then trying to assemble that into a geometric form which would describe a uniform color space. And you can see from these diagrams, it's a complete, utter failure. And color scientists tried this, it failed. So where that effort headed was then to try to find a geometrical form that would take the original space of CIE little x, little y, and here you can see little y numbers, and I hope somewhere you can see little x numbers. Yeah, here's little x numbers, but the little x numbers sort of radiate from this point because this color researcher, who I think is not Ed, David Kelly, I think is the guy's name, figured out this transformation, which of course we're all computer graphics guys, so we recognize this as kind of a perspective transform. So you cannot do this transform in a 3x3 matrix. In mathematics terms, 3x3 matrix is one example of an affine transform, but what I'm showing here is not an affine transform. This is, in mathematical terms, a projective transform, which is the same sort of transform that describes perspective. And if you look really carefully, you can see, well, wait a minute, these lines are sort of radiating. Also, it's just that their focus point is way off the screen here. So it's a perspective transform with two vanishing points. And this scheme worked reasonably well to take that huge area, which was the greens, and kind of compress that into a smaller set of coordinates, and also take that red area and basically expand it out so that those colors that started in the little tiny region of the diagram, they now cover a reasonable area. So the goal here is make a diagram which has perceptual equal areas for coordinates that we see as being roughly the same color. Now, this diagram that I've just shown you, if you read carefully down here, it's the UV diagram. And this one was made in 1960, but basically there was an improved one made in, I want to say 1976, and it's called U prime V prime. Now the primes here are not exactly the same primes as the RGB primes. However, like RGB prime, this scheme is trying to be perceptually uniform. So this is also known as CIE LUV space. Now, it turned out to work well, but there's another space, and that's CIE lab space, and its coordinates are L star, A star, B star, and it works better. So basically, CIE love is obsolete, and lab is the one we use. But it's a transformation roughly like this. So now, having done that bit, let's see where we go, because I can't remember where we go. Oh, here's the arithmetic for LUV space. And you can see these division operations. That corresponds to the projective transform. And that particular constitution of those denominators, that fixes where the vanishing point is. So you can have various transforms, and we just picked the one that's got the vanishing point that we like. Now, the better system is L star, A star, B star, also known as CIE lab, as I mentioned a moment ago. So you can jam that together, or you can separate it It just depends on style. All of those mean the same thing. Now, you can see from the equations here that basically what's going on is we're taking the big X, which is sort of loosely related to red, and the big Y, which is the luminance. Sorry, let me pick a slightly contrastier color. The big Y, which is loosely related to the green, and the big Z, which is loosely related to the blue. And that little denominator here, that's just a normalization factor. So if you've normalized correctly between 0 and 1, then you can ignore those denominators completely. So what you've got here is x to the 1/3, y to the 1/3. So x to the 1, and I'm sorry, I need to pick a better color. And not that one, that was just my eraser. Let's pick this one. So what you've got here is basically big X to the 1/3 and big Y to the 1/3 subtracted. And then they're multiplied by a fairly big number, but we'll get to that in a minute. Now, take a look at those terms and think about, for a minute, x to the 1/2.6 and y to the 1/2.6. That's digital cinema coding. Digital cinema coding has got 2.6 gamma. Now, I'm putting it in quotes because here we're using the reciprocal gamma. This would be digital cinema encode. And then x to the 2.6, y to the 2.6, z to the 2.6, that would be digital cinema decode. So these terms that are used to form A star, B star, they're sort of the color version of a perceptually uniform space. And digital cinema encoding is absolutely a perceptually uniform space. Now, we've got x to the 1/3, x to the 1/3 minus y to the 1/3. That subtraction makes it a color difference. So we've already got the L star term. That's the luminance information has been encoded into that. Basically, L star is approximately y to the 0.42. So this serves as perceptually uniform coding. So we've got LAB perceptually uniformly coded into two components. So we can draw diagrams that show lab space. And the A star and B star components roughly go plus minus 100. So you can think, well, okay, then if there's 200 by 200, that should say that at every luminance level, there's 40,000 colors. And if L star is represented 0 to 100, that means that there's 40,000 colors at each level. Times 100, there must be about 4 million colors. And guess what? There's about 4 million colors. So there's your back of the envelope calculation that says, how many colors are there? Answer, about 4 million. Okay. Now, you can, this is a fancy looking equation, but it's actually very simple. This delta EAB is just the difference of two L stars squared plus the difference between two A stars squared plus the difference between two B stars squared, square root of the whole thing. This is called the root, and the plus here acts like an average or mean, and these elements are squared. An electrical engineer would call this root mean square, but a VFX guy might think, well, that's simple. That's just the distance across a cube. That's Euclidean distance. So this formula allows you to compute the perceptual distance between two colors. And L stars range from 0 to 100. A star and B star range plus minus 100. I've explained that if you multiply all those out, there's about 4 million colors. And a delta E star of less than 1 cannot be seen by anybody. Now, if delta E star is somewhere between, let's say, 1 and 5, maybe you can see it, maybe you can't. It depends where you are in color space. And if 5 is less than delta E star, or in other words, delta E star is bigger than 5, that's a problem. That color shift is so large, it's very likely to be noticeable. So this whole delta E star business, which is of course built on lab space, gives you a way to measure color errors. And if you have got monitor calibration or projector calibration happening in your facility, your calibration expert, which, well, maybe one of you, any of you guys attending, your calibration software will be reading out delta E numbers. Now, you have to take them with a grain of salt because I can't tell you exactly where in color space delta E needs to be, less than 1 or less than or equal to 1, and where you can get away with delta E of 2 or 3. It all depends exactly where you are in color space. But that's the whole reason for lab space. So now let's go one step further. So that's the end of that section. So I'm delighted that that's the end of that section. I think on class 1, I gave you an introduction to color transforms. So I'll give you the very quick preview here. Here's the sorts of things we're going to be looking at next class. Now, I'm not going to go over these in huge amounts of details, but I want you to know by next class how to convert one RGB system into a different RGB system by using a 3x3 matrix transform. That's where we'll head to. And so with that, we're at the top of the hour. Let's see, I've got 59 minutes. Let's see if we can squeeze in one question. If anyone wants to type in a chat question or even pipe up in audio with a question. Peter's asking, could we touch on my comment in the forums that all projectors in the field today are set to P3 RGB? And that's a good question, and let me address that now. I guess I should have included the phrase digital cinema projectors, because all of the DLP cinema and SXRD cinema and even DILA cinema, they're all delivering P3 gamut and not much more. So let me give you a little sketch about how that works. Basically, if you've got the ability to generate light from 400 to 700 nanometers, the amount of light that the human vision system will see is weighted by the human vision spectral sensitivity. So there's an important curve. We usually call it little y bar, and that's the luminous efficiency curve of human vision. So how how bright something looks is weighted underneath that curve. And that curve goes from 400 to 700 nanometers, and it peaks at about 555. Now, you can choose to generate light like this for green, or light like this for green. What matters is the area under the curve. So this green might be typical of a CRT phosphor, and this spectral power might be typical of a laser. In fact, lasers sort of look like this. They're highly, highly, highly concentrated. But the brightness that you see is the area under the curve. So for engineering purposes, it's generally easier to produce light that looks like that than it is to produce light that's got a power distribution that looks like that. Now, on the flip side, in terms of the famous CIE chromaticity diagram, we have the Rex 709 region looking something like this. You might think, well, we really want to get a highly saturated green, but you have to go to that sort of laser power to get there. And it's particularly a problem if you start with a light source, and here I'm trying to sketch a xenon light bulb. So let's say this is a 6 kilowatt xenon bulb, which is bright enough to light a big projector, and it's got a distribution that looks sort of like that. Well, you can't just slice out a little tiny piece of that light and use it out here. Economically, that would involve throwing away all of that light. And so to make a really bright projector, you're forced to use a fair bit of that power, split that off into the blue channel, a fair bit of that power in green, and a fair bit of that power in red. Now, some of you might have heard about the cyan notch filter or the yellow notch filter in a DLP projector. These are optical filters that are actually throwing away light from the xenon in order to get color reproduction, which has got the primaries moved out. But they're throwing away light, they're throwing away brightness. So the practical situation in the field today is that DCI, digital cinema projectors, are using these DCI primaries. This one, sorry, I'm a little out of line. This one, the blue is actually identical to HD blue. The red is out here pretty much right on the spectral locus. So digital cinema projectors are in practice all using the P3 gamut. And there are certain colors that they can't reach. Now, when we get to laser projectors, you can think, well, okay, if I had a laser projector, then I could pick a green that was up here, and that will get more of those colors, maybe not all of them, and more of those colors. And I could even pick my laser down here and down here. Well, you won't pick them down there, because if you pick laser primaries down there, they are so far down that curve that they're really, really inefficient. So you kind of have to come up a little bit along the spectral locus up into this kind of range. And also you can see from this diagram, I think, that where you pick the green primary, if you pick green over here in order to get these colors, you've then lost some colors in this interval. So it's very tricky business picking the primaries. And some of you might be thinking to yourself, well, gosh, it seems pretty clear that what we should do is we should have a 4 primary system, and then we can get all those colors. That's absolutely feasible, but not really practical and economical today. Now, there is one example in commercial space of an LCD projector which does that. That's Sharp. And they picked the fourth primary to be yellow. And, personally, I think that was not really getting the sort of improvement that you could get, but Sharp gets to do whatever they want to do. So there's the technical background behind the common P3 space that everybody in digital cinema is using today. It's just kind of an economic imperative, and how we get to wide gamut is very much up for grabs. So there you go. There's the end of Class 5. I'm having a great time doing this. I hope you're enjoying it too. However, we've come to midterm break time. My daughter, who's in university, and her boyfriend are going to fly to Cuba. Lucky them. She's got a part-time job that allows her to do that. Whether you're going to fly to Cuba or vacation, I'm not sure. But in any event, no class next week. And watch the forums and watch your email for the timing on Class 6 in 2 weeks. I'm not sure whether that's optimized for the Europe, North America portion of the world or the Asia, Australia portion of the world. But watch the forums, we'll find out. Thank you very much for participating. See you in 2 weeks.